Yay!
Yay! Let's do an example of a magnetic field calculation for a moving point charge, because it's when you have charges in motion that you get magnetic fields. All right, so let's take the simplest example that we can. So suppose I've got a positive charge plus Q, and at some instant, we'll call that the origin, and it's moving in the plus X direction, let's say. And what I want to do is calculate the magnetic field at different points, almost sort of where your compass would point. And at first, let's just do the direction, because that's sort of the main obstacle with calculating magnetic fields, is they're just weird. And it's hard to have a good sort of an intuition about what way they should point. Electric fields are easier. If you got a charge, like a positive charge, it's easy to imagine an electric field radiating away from the point charge in every direction. That's easy to picture. The magnetic field is not so easy, because there's this kind of bizarre cross product. So let's see if we can get a little bit of intuition about what it should look like. Okay, first of all, what I'm going to do is calculate the magnetic field at different points. Let's say A, B, C, D. Just to keep it simple, suppose that these points are all the same distance away from the origin, R or whatever. So let's see what the magnetic field should look like at these different points. How are we going to do it? We write down a version of the Biot-Savart equation. Anyway, it's sort of like Coulomb's law for the magnetic field, and it looks like this. The magnetic field is, okay, remember that the electric field was kq over r squared, right? That was its magnitude. And the k was that electric constant that was like 9 times 10 to the 9th. But really, you write it in terms of a more fundamental thing, 1 over 4 pi epsilon naught, right? We had like this. The electric field magnitude was kq over r squared. K was 1 over 4 pi epsilon naught, like that, right? The magnetic field is the same kind of thing. There's a different constant. There's sort of, if you want, you could think of it as a magnetic K, written in terms of a fundamental magnetic constant, which is called mu naught. So it's mu naught over 4 pi. That combination of things is sort of called the magnetic K, if you like, and it's got a value of 10 to the minus 7th in some complicated units. But anyway, that's the number that you plug into the calculator. So it's pretty easy. Like for electric fields, it was 9 times 10 to the 9th, right, for that K. All right, so that's 10 to the minus 7. K, and then it depends on what the charge is, Q. And there's also a 1 over r squared. That's nice. So far, it looks a lot like the electric field. If it were the electric field, you would have that r hat, right, indicating that it's a radial field away from the charge. But what we have here is not that. What we said was the magnetic field is it depends on the charge is moving. It's a moving charge that generates magnetic fields. So somehow the movement of the charge has to be in here, and that would be the velocity. So I got to put the velocity in here, and it's a vector, right? So I got my v, so that's got to be in there, but it's in there in a really complicated way, and I'm just going to write it down. Cross r hat. It's not really obvious what that's going to mean or what that's going to look like. That's one form. I could also write it like this. This is how I'm actually going to use it in calculations. It's going to be mu naught over 4 pi. I'm going to have my Q. I'm going to take the V, the magnitude of the V outside. So it's QV over, and then I'm going to keep that R squared on the bottom. And so what I'm going to have inside here is I'm going to have V hat cross R hat. That's just going to be a little bit easier to deal with. Notice V hat cross R hat, that's the product of 2 unit vectors. So that's going to be another unit vector. So this thing out front, that thing is going to be the magnitude of the magnetic field. I'm just going to call it B naught. And that's going to be in Tesla, the SI unit of the magnetic field is in Tesla. So the magnitude of the magnetic field is going to be given by that. And then I'm going to have this crazy thing that's going to give us the direction, V hat cross R hat. Okay, it's a cross product, right? So if it's a cross product, I'm going to need to use this. A long time ago, oops, that's like an oval. A long time ago, we talked about the cross product and how you actually calculated X, Y, Z. And you might have been shown in math class or something that the cross product is like a determinant, right? It's a 3x3 determinant of a matrix. But that's, I mean, that's no good. You don't want to calculate that. And even worse, you don't want to try to memorize the thing. So what I do is just generate it. So the cross product of A cross B, I just use this little diagram. The diagram just is a little cycle, X to Y to Z. It's called a cyclic permutation. So what you do is you just follow this thing. I'll use my laser pointer. You just follow the cycle around the cycle. So if I want to know the X component of the cross product, I just go X to Y to Z. The X component, you start with A, Y, B, Z minus, and then you flip it, A, Z, B, Y. So this tells you how to write down those first two terms. If I want the Y component, I just go around the circle. That would be A, Z, BX. A, Z, BX minus A, X, B, Z. And then if I want the Z component, I just follow around the circle, A, X, B, Y. A, X, B, Y minus A, Y, BX. Nice. And the advantage of that is that I can just generate it. Once you kind of practice a couple times, you just can write it down as fast as you can write it down. You just generate it when you need it. That way I don't have to memorize it, because I would always talk myself into thinking that I memorized it wrong. Okay, so there's the cross product. That's what we're going to use. Okay, so back up to the diagram. Let's do the cross, or let's evaluate the magnetic field at all those points. How about A? Here's how we're going to do it. At A, what do I have? The magnetic field at A is going to be, well, I got all that junk out front, right? But I called that B naught. So let's just say it's some number, some magnitude of magnetic field. And then I've got the direction. V hat cross R hat. Okay, well, in this example, my V hat, that's always going to be in the X direction, right? So this is just going to be X hat cross. And now my R. Okay, this is defined in the same way that it was for the electric field. The R hat is always the direction from the charge to the point you're interested in. Always, always, always. So in this case, from the charge to A is just in the X direction, right? So this is just going to give me X hat cross X hat. Well, any vector crossed with itself is going to be 0. Right? So that's just a sort of an identity. So this is just going to be 0. No magnetic field at A. Okay, how about B? At B, the magnetic field, again, I'm going to have this B naught. My V is always going to be in the X hat direction, so I can just always just write that down. Okay, now what's my R? To get from the charge to B, I go in the Y hat direction, right? So what I can do, X hat cross Y hat. Okay, there's a couple of ways you can do this. You can go ahead and multiply it out. You can just take the cross product. What is X hat is just 1, 0, 0, and Y hat is 0, 1, 0. And if you just take the cross product the way we wrote it down, component by component, what you wind up with, believe it or not, is you're going to get that. It's good to check if you've never done it before. It'd be good to check. But there's a shortcut. The shortcut is, again, you can use this little cycle, because this little cycle also tells you what the hat cross products are just by looking at it. It's pretty neat. So you just go around the circle. X hat cross Y hat is Z hat. Y hat cross Z hat is X hat. Neat. Z hat cross X hat is Y. So if you're going around the circle in that clockwise way, you get a positive cross product. If you go around the other way, you get a negative sign. So X cross Z is minus Y, right? Z cross Y is minus X. So that's how you can use that diagram, not only to generate the components of the cross product, but also to do the crosses of all the unit vectors. That comes in really handy, so you don't get confused. So in this case, X cross Y is Z. So the magnetic field I guess I'll use green. The magnetic field is just pointed in the z direction. That's interesting, right? It's kind of an odd field. Okay, next. What's the magnetic field doing at C? That's going to be B naught. I got X hat cross. Okay, from the charge up to C is going to be Z hat. I got my Z hat. What is X cross Z? Okay, I come over here to the little wheel. X cross Z is Y. And I'm going around backwards. So I'm going to get a minus sign. So it's going to be B naught minus B naught Y hat. So it's going in the minus Y direction. Oop, like that. Well, that's really strange. Let's do D, and then we'll start to get a clear picture. The magnetic field at D is going to be B naught. What the heck is that? It's going to be B naught X hat cross. To get out to D, I have to go negative X hat. Okay, well, that's negative a vector across itself, which is going to give me negative 0. It's still 0. All right, so along the axis, along the direction that the charge is moving, there's no magnetic field. That's cool. That applies to a train of charges. Then suppose we have a wire, right, with a whole bunch of charges going in the x direction. So a current going in, we'll follow up on this soon. If we have a current going in the x direction, there's no magnetic field in that straight wire, right? It's only in the points around the wire. Okay, let's do E. So the magnetic field at E, let's see, this is going to be B naught, and it's going to be X hat cross. How do I get from the charge to E? I go in the minus Y direction. So we've already done X cross Y, that's Z, and then I got a minus sign, so it's minus B naught Z. Okay, so it's going in the minus, it's going in the minus Z direction. E. Now that's starting to look kind of interesting, right? I can sort of predict then, look at what the magnetic field is doing at B and E. I can sort of predict then what it's going to do at F. I might predict that it's going to be going that way. All right, let's see. At F, the magnetic field at F is going to be B naught X hat cross. How do I get down there? I go minus Z, right? So X cross Z, I already said was minus Y, but now I got another minus sign. So it's just going to be plus B naught Y. So sure enough, it's going in the plus Y direction. So what's neat is that I've built up this picture that as the charge is moving in the X direction, I have these magnetic field lines all around it. And in fact, it might be a good idea if you pick points in between that have a mix of X and Y. What you're going to find out is that you get this sort of a circle. Those magnetic field lines, it sure doesn't look like it the way I've drawn it, but those magnetic field lines are everywhere tangent to a circle. So the magnetic field has arrows that sort of circulate around the moving charge. And the direction is given by the right-hand rule. So the shortcut is, if you have a charge moving in a particular direction, and this is true of currents too, we'll come back to this, but if you have a charge moving in a particular direction, you put your right thumb in that direction, and then the curling of your fingers indicates the sort of the orientation of that circle, which way the circle is curling around that current. Okay, so those are the directions of the magnetic field around a moving point charge. We can also use the same idea to calculate if we want. This also means I can calculate the magnetic field at any point in space that I want. So for example, let's choose some other color. Suppose I'm out here in space. I'll give it some X, Y, and Z coordinate, maybe up there, right? Is that good? Okay. So up here, let's say that this is located at 4, 4, and 7. 4x, 4y, and 7z. So just some arbitrary point out there. Let's figure out what the magnetic field is at that point P. I can stick in a particular point if I want. For this, I'm going to write the magnetic field again slightly differently, just to make it a little easier to calculate. This magnetic field is going to be mu naught over 4 pi. I'm going to have a Q. Again, I'm going to take out, oh, actually, I'll leave that in. Q over R cubed. This is kind of the same trick we used for the electric field. If I make that 1 over R cubed, then in the parentheses, I can have my V cross R vector. I can make both of those vectors, right? Because R hat is just R vector over R. So I just made that little substitution. So now let's suppose, what did I use in here? Let's say Q is 10 nanocoulombs. Let's give it some speed. What did I say? 1,000 meters per second, 10 cubed meters per second. And in this case, R, it's I think what I said was it's 447 centimeters. So R is 9 centimeters. That's in centimeters. It's kind of neat. If you do 4 squared plus 4 squared plus 7 squared, and you take the square root, you get 9. It's sort of a Pythagorean triplet. I think that's what it's called. Anyway, so you get a nice even number at the end. Okay, and then my V cross R. Okay, so I'm going to have, what is my V cross R? That's going to be the vector of 1,000, 0, 0, because I just have it moving in the x direction, crossed with, I'm going to have, these are centimeters, 0.04, 0.04, 0.07. And then if you carry that out, the only thing that matters, it turns out, is the y and the z component. If you look down here, anything involving ay or az is going to go away, right? So I got none of that, none of that, none of that, none of that. So I have minus axbz, minus axbz. So that's going to be, that's in the y component. So it's going to be minus 40. I'm sorry, 70, right? Minus 70. And then axby, the z component, axby, you always have to be careful doing this stuff, 40. That's what you get there. Okay, so that's the vector. That's V cross R. So I would just multiply that times my mu naught over 4 pi, which is 10 to the minus 7, right? And then my Q, which is 10 to the minus 8. R cubed, 9 centimeters cubed, remembering to convert it to meters. And what you wind up with, calculations are boring, so I'll let you do it if you want. But believe me, what you get is 0. And then I got a minus 96, and then I got a 55 times 10 to the minus 12 Tesla, or picotesla, is the magnetic field at that point. So it's got both a y and a z component. But anyway, that's the way that you would figure out the magnetic field at any point. You just pick any point you want, and then you know the r, so you can plug the r in there, the r vector, and the v could be any arbitrary speed or any arbitrary velocity too, right? You just have some speed going that way and some point that's out here. As long as you know what those vectors are, you can plug them in, and then you can calculate the magnetic field there. Okay, so that's what the magnetic field from a moving point charge looks like and how you would calculate it. Most of what we're going to encounter, though, is going to be currents. It's rare that you'll have to figure out the magnetic field from a moving point charge, but it's pretty easy then to generalize from a moving charge to then a current, because what's a current but just a whole train of moving charges all going in one particular direction. So that's what we're going to do next.